Hello students, welcome to our new unit on thermal energy, and in this first video lecture we're going to talk about the difference between three concepts that we tend to use very interchangeably in everyday speech. So thermal energy, temperature, and heat. Usually these last two, temperature and heat, we kind of speak of as if they're the same thing, but we're going to learn that they're not and figure out the important differences between the two. So that's our first objective, which is to explain the difference between temperature and heat and how those are different from thermal energy. So these are three different concepts. We also want to be able to understand the connection between molecules and temperature. There's something going on in the molecules of a substance that relates to its temperature, and we're going to find out what that is. Third, we want to be able to identify standard temperature scales. How do we measure temperature? What does it mean to measure temperature? What are we actually measuring? What does it physically tell us about a substance? And finally, we would like to be able to convert temperatures between the three standard temperature scales, which are Celsius, Fahrenheit, and Kelvin, as mentioned in this lecture. Before we begin, it's useful to think about what is actually happening if we zoom in really far on substances, whether they be gases or liquids or solids. So a gas or liquid, let's say air. Air is a gas, and if we were to zoom way in on air, we would see little molecules of air. They're nitrogen, carbon dioxide, oxygen, whatever they are. These molecules are sort of zipping around, and they're kind of randomly moving around in all directions, bumping into each other, and just sort of jostling about. And when the gas is cool, that is, when we say it has a low temperature, what's happening is that these molecules don't have a lot of movement. They don't have a lot of kinetic energy. So they're moving pretty slowly and don't have much in the way of that kinetic energy. Over here is a diagram that shows hot gas, where it's at a higher temperature, and we can see that these molecules are moving around much faster. And this is going to give us the key to understanding what temperature and thermal energy are. Already you can see that there's some connection between the motion of the molecules and the temperature of the substance. And this is also the case in a solid. Now, in a solid like wood or stone or plastic or anything that is a solid object, the atoms are not flying around, but you can think of them as being sort of stuck together by springs. And this isn't literally what it looks like. There are not literally springs inside of every solid object, but that's kind of how atoms behave. They sort of jiggle around in place. This atom is going to sort of vibrate around, and this atom is going to vibrate around, and they're connected by these intermolecular forces, which are represented by strings, but they're still moving. And that jiggling around, that vibration, is still kinetic energy. And in a solid object, when it's at a higher temperature, these atoms are going to vibrate more and more. And so we still see a connection between motion of molecules and the temperature of a substance. So let's take some notes that will solidify some of these concepts, and then we'll look at a couple examples. So first of all, what is thermal energy? Thermal energy is going to be the point of this entire unit, so it makes sense to define it first. Thermal energy, before we talked about it just being sort of heat energy or energy associated with something that's hot or has a high temperature, and now we're going to give it a very specific definition. Thermal energy is a measure of the total kinetic energy of the molecules that make up an object or substance. And remember that kinetic energy is the energy of motion. So this should be a little bit surprising to you, that thermal energy, which we learned early on in the school year, is a different kind of energy than kinetic energy. Now we see that if we zoom way in on something, thermal energy is just secretly kinetic energy. It's the kinetic energy of the molecules that make up something. And the more thermal energy something has, the faster those molecules are going to be moving. So thermal energy is stored in the motion and vibration of molecules. It's motion when it's a gas or a liquid, and it's vibration when it's a solid, mostly. But you can think of it as just motion or movement or vibration. So here's a definition of temperature that is slightly different. It measures the average kinetic energy of the molecules that make up an object or substance. Notice the difference. Up here, thermal energy was measuring the total kinetic energy of all those molecules. Temperature is measuring the average kinetic energy of the molecules. A way you can think about this that helps make that a little bit clearer, I hope, is to think about it in terms of this question. How much thermal energy would each molecule have if the thermal energy was shared equally among all molecules? That's a way of thinking about temperature. It's not the total amount in the whole object. That total amount of kinetic energy of the molecules is thermal energy. It's what is it on average per molecule, and that's going to be what we call the temperature. And I'll give you an example on the next slide that will help us differentiate the two a little bit more clearly. Before we do that, let's get one last definition, and it's going to be heat. Now, we said we're going to learn the difference between these three terms, thermal energy, temperature, and heat. And here's the final definition between these three. Heat is the transfer of thermal energy from one object to another. In an earlier unit, we learned that energy moving from one object to another is called energy transfer. So when we move thermal energy specifically, we call it heat. Just like when we moved mechanical energy from one object to another, we called it work. And when we moved electrical energy from one object to another, we called it electricity or electrical current. Now, thermal energy, when it moves from place to place, it has a specific word, heat. Notice, heat is a process. Heat is an action. It is not a thing. So you can't say this object has more heat than this other object. Heat is actually the flow of thermal energy between the two. Okay, it's a process. It's something that's happening. Heat is an action. Let's take a look at an example which might help us think about the conceptual difference between thermal energy, temperature, and heat. So this diagram shows two pots of water, and this pot here on the right has far more water. It has twice the water as the pot here on the left. Now, both of these pots of water we're told boil at 100 degrees Celsius. This is actually the temperature at which pure water boils. So here we have an example of what temperature is. Okay, we are measuring a temperature in both of these pots. The water molecules on average are vibrating the same amount, and we're going to measure that by calling it 100 C. But if you look at how much water we have, there's way more water over here than over here. So if these molecules are vibrating the same as these molecules over here on average, then overall, in total, there is much more vibration going on over here than there is over here. And that is what we call thermal energy. So let me make a note here. Oops. Go with my text. More thermal energy is going to be on this side of, on the right-hand side here. It has more thermal energy because there's just simply more molecules that are vibrating at the same amount. Okay? And how are we getting thermal energy into each of these pots? Where is that energy coming from? It's coming from these flame jets down over here, and those gas jets are adding thermal energy to the system, and they're doing so by applying heat. They are moving thermal energy from the burner to the pot, from the burner to the pot over here as well. And that transfer of thermal energy is called heat. So let me continue labeling. I said that this one is more thermal energy. I'm going to move a label over here and say less thermal energy. There's less thermal energy because there's less mass. There's less water over here that is at the same temperature. So once again, they're vibrating. The molecules are vibrating on average about the same in both of these pots, but there's just more of them over here. So even though they're at the same temperature, they have more thermal energy on the right-hand side. So now that you have that example to help you understand the difference, go back to your notes and annotate on the left-hand side with any new insights that you have, connections or examples that you'd like to add to your notes that help you understand thermal energy, temperature, and heat. Here's an example. Both of these objects have a very small object and a very large object. Both of these objects have the same amount of thermal energy. Which would have the higher temperature and why? What I'd like you to do is pause the video, think about this question, answer it for yourself, and then restart the video so you can get the answer. Well, let's see how you did. So both of these objects, I have a small object and a large object. We are told that they have the same amount of thermal energy, which would have the higher temperature. So imagine all of this energy. It's the same amount of energy. Let's say it's 100 joules, whatever it is. And 100 joules over here concentrated in far fewer molecules than 100 joules over here. Imagine all the molecules here and all the molecules over here. If they had to share that 100 joules, where would we have the most amount of energy per molecule? Well, that would be over here in the smaller object, because that same 100 joules of energy has to be shared by less molecules. So on average, each molecule is going to have more energy. So how would we sum that up? Let's say the smaller object will have the higher temperature because the same amount of thermal energy will be shared by fewer molecules. Therefore, the average kinetic energy of the molecules will be higher in the smaller object. And average kinetic energy, remember, that is our definition of what temperature is. Okay, so now we can say that between these two objects, higher temperature is going to be over here on the left-hand side. Now let's think about temperature scales, and this means how do we measure temperature? There's a lot of good reasons to measure temperature. We might want to know something as simple as, well, how hot is it outside, and what kind of clothing should I wear for the weather outside? That's a pretty mundane example, but it goes all the way up to, well, how do we design devices that can withstand the amount of heat of a computer processor, for example, or insulation in homes, or even re-entering spacecraft, which get very hot as they get back into the atmosphere. So there's a lot of good reasons to be able to know the temperature of a substance. And the first kind of temperature scale is something that we are probably pretty familiar with, and this is how we measure temperature just sort of on an everyday basis. And this is called a relative temperature scale. We call it relative because it's a scale for measuring temperature that is relative to common phenomena, things that happen in everyday life. So the two most common relative temperature scales that you're going to find are called Celsius, and Celsius is the one that is most commonly used in countries besides the United States. I think we're the only country left who uses Fahrenheit. But Celsius is the everyday temperature scale for most of the world, and it is based on the freezing and boiling points of pure water. And we're going to find that on the Celsius scale, 0 Celsius is going to be where pure water freezes, and 100 Celsius is going to be where pure water boils. And we just have 100 even units in between those 2 points. Water is a pretty important substance to people and to most life on Earth, of course. So it's something that's all around us. It's in our everyday experience. Why not make a temperature scale based on those phenomena? Now, the Fahrenheit scale is a scale that we are used to here in the United States, and it is based on natural phenomena. It is not random. It is based on the freezing point of salt water, that's 0 Fahrenheit. So not pure water, salt water freezes at 0 Fahrenheit. And Daniel Fahrenheit, back in his day, the average human body temperature was, as near as he could measure, 100 degrees Fahrenheit. And we know better now, a little bit more precisely, that the average human body temperature is 98.6 degrees Fahrenheit, but in his day, the average human body temperature was 100. So he set the 2 points on his scale, 0 at freezing point of salt water and 100 as the average human body temperature, and he developed his 100 even units between those two common phenomena. And we can convert between these two using some very simple equations. TF in these equations represents the temperature in Fahrenheit, and TC represents the temperature in degrees Celsius. And you can find, if you know the temperature in degrees Celsius, you can get to degrees Fahrenheit by multiplying the temperature in Celsius by 9/5 and adding 32. And you can do a little bit of algebra and reverse that process to find out how you can get degrees Celsius from degrees Fahrenheit. So these are pretty easy, and if you ever travel abroad, you may want to use those to transfer between Celsius and Fahrenheit. What I have down here is just sort of a graphical side-by-side look at these two temperature scales. I have Fahrenheit on the left. Again, this is what we're familiar with in the United States. If we say it's a pleasant day outside, it's 70 degrees. That's it's about somewhere here on these scales. But someone from the UK or Europe might say that a pleasant day is 20 degrees. And we certainly wouldn't like that here on the Fahrenheit scale. 20 degrees would be well below freezing. But the point of looking at these side-by-side scales is to notice that nature doesn't care what number we put on these phenomena. Water boils when water boils. Whether we call it 212 Fahrenheit or 100 degrees Celsius or whatever else, it doesn't matter. Water boils is a natural phenomenon at sea level, and water boiling at sea level occurs at this temperature. And in the Fahrenheit scale, we call it this number, 212 Fahrenheit. And in the Celsius scale, we call it 100 degrees Celsius. Water freezes at the same temperature at the same altitude and conditions. So pure water freezing under the same conditions is going to be 32 degrees Fahrenheit or 0 degrees Celsius. Here's dry ice, which is made up of carbon dioxide, solid CO2, and that happens at negative temperatures on both scales. And here is absolute zero. And we're going to talk about absolute zero on the next slide, but this is about as cold as you can get. Not about as cold as you can get. It is as cold as you can get. Absolute means the final, as far as you can go, zero. So the coldest you can possibly get is about negative 460 degrees Fahrenheit and about negative 273 degrees Celsius. So what does it mean to be at absolute zero? What does that even mean? Well, let's consider. Temperature is a measure of how fast molecules are moving or vibrating. So let's imagine if we took those molecules and we slowed them down, and we slowed them down, and we slowed them down even more, even more, even more. And we're making it colder. So when we remove kinetic energy, when we remove motion of molecules, that's what it means to make something colder. Let's say that we remove all of their molecular motion. We make them stop completely. They're not moving, they're not vibrating. What we have achieved then, in that case, is called absolute zero. It is the coldest possible temperature. You cannot get any colder in the universe because of the way we define temperature. If temperature is related to the motion of molecules, and you take away the motion of molecules, then you're out of temperature. There's nothing left. There's nothing below there. So sometimes we want to have a scale that measures the temperature relative to absolute zero. Remember that what we had back here was a relative temperature scale. It was relative to everyday things that are kind of important to human beings, like freezing and boiling of water, or human body temperature, freezing of salt water. Humans care about these things. The universe generally doesn't. So the universe cares about things like absolute zero because that's sort of a universal thing. So sometimes in science, it makes sense to have what's called an absolute temperature scale. And this is a temperature scale that begins at absolute zero. It is impossible to have a negative value on an absolute temperature scale. The first one is Kelvin, and we're basically using the same scale as Celsius, but we're just redefining what zero is. We're moving zero to absolute zero, and then each degree is the same as Celsius, basically. Rankine is a temperature scale that we don't really use much anymore. Very limited applications in engineering and some old data tables and old reports sometimes use Rankine, but in general this is kind of useless. So we won't really talk about Rankine much, but it's essentially the same thing as Kelvin in the sense that 0 degrees Rankine is absolute zero, and each degree is the same size as Fahrenheit instead of Celsius. So to see what that kind of looks like, you can look at this scale here of Celsius and Kelvin, and you can see absolute zero. This is, again, the coldest possible temperature in the universe is out here at negative 273 Celsius, and it's just 0 K, 0 Kelvin. And the same steps are there for Kelvin and Celsius. Each degree is about the same size. So if negative 273 Celsius is 0 Kelvin, then 0 Celsius better be 273 Kelvin, because all we did was just sort of slide this scale downward to get Kelvin. Water boils at 100 degrees Celsius, as we said. This is pure water boiling at 100 C. And if we want to find the value in Kelvin, all we need to do is add 273.15, or we can just round this usually to 273. But that gives us 373 Kelvin as the boiling point of water. So that's an absolute temperature scale. So this is kind of a fun fact, looking at protractor, which we use to measure angles, and angles we also measure in units called degrees. We normally think of those things as separate. Well, what do degrees of angle have to do with degrees of temperature? Well, think about where water freezes on the Fahrenheit scale. It's about 32 degrees, so just like something like that. And where does water boil on the Fahrenheit scale? Well, it's 212 degrees Fahrenheit, which is something like that. And what you have is a 180 degree line between freezing and boiling of water on the Fahrenheit scale, which is kind of cool. So connecting degrees of angle to degrees of temperature in a sort of an odd geometric way. Okay, before we wrap up here, I want to show a quick video, and I just found this on YouTube, but it's pretty cool. It's showing what molecules look like of water vapor, and you can see them zipping around very quickly. And as we lower the temperature, what's happening is the molecules are getting slower and slower and slower, and they keep slowing down as we lower the temperature. And remember that temperature is this measure of average kinetic energy of the molecules. And look, they're speeding back up, and the temperature is rising as they do that. It's a neat little graphic that helps differentiate between these three concepts and illustrate the connection between molecules and temperature. So our objective, the difference between thermal energy, temperature, and heat. You should be able to understand the connection between molecules and temperature. Again, motion of these molecules results in a higher temperature. And identifying standard temperature scales. How do we measure temperature? in Celsius, Fahrenheit, and Kelvin. You don't need to worry about Rankine because nobody really uses Rankine. But can you convert between temperatures that are given in Celsius, Fahrenheit, and Kelvin? If you're given a temperature in one, can you convert to the other? And you can do that using the equations that were mentioned in this lecture. Okay, thanks for listening.